Thanks a lot, everyone of you for coming. Thanks to the organizers for inviting me to this, what promises to be a really exciting program. So welcome back to this submodularity tutorial. I hope you won't suffer too much from diminishing returns. So in the second part of this tutorial, as Stephanie promised, we're going to talk about submodular function maximization, which is going to exploit some of the concavity-like properties of submodular functions. And if you have time, we'll talk a bit about some advanced topics towards the end of this tutorial. So let's get started. So we're talking about submodular function maximization. Just a quick reminder of the setup. So we'll have some ground set of items that we want to select from. And we assume that we're given, in terms of oracle access, some submodular function f that takes subsets of those elements and scores them. And for maximization, this function is typically going to be interpreted as some form of utility, which we aim to maximize. And so we want to maximize this function over this ground set, typically subject to some constraints. So Stephanie already talked about some applications. Let me just give you a bit of a reminder of some motivating applications. So a large class of submodular function maximization problems are motivated from the perspective of optimal information gathering. So for example, Stephanie talked about optimally placing sensors. Other problems of that kind are, for example, telling robots where to go in order to collect informative measurements. Similar problems arise, for example, in optimal experimental design. They are given a collection of possible experiments we can conduct, and we want to select a subset of those that are most informative with respect to what you want to learn. Other examples in machine learning, for example, come from active learning. They might given a large collection of unlabeled data points, and we want to select a subset of those points to get labeled in order to fit, say, a good classifier. Okay, so that's one type of problems where we want to maximize submodular functions. And here, the set function f typically is some notion of information, informativeness. And you've seen some concrete mathematical examples of this in the first part of this tutorial. So the other motivating application that we'll be talking about is this notion of data summarization. So we might be given a very large data set that we already have acquired, and we somehow want to select a subset of it. There's many motivations for this. So in exploratory data analysis, maybe we want to identify some representative subset of elements. Maybe we've got a large collection of images that we took on our last vacation, and we want to come up with a summary, or we took a video and we'd like to extract short parts of that video in order to summarize our experience. Another type of data summarization problems that has received attention is the problem of data subset selection. So suppose we want to train some deep learning model on a very large data set. So if we train it on a big data set, maybe with hundreds of millions of data points, we might take a long time on our compute cluster. So what if we could just select a representative subset of our training data that's much smaller but still indicative of the entire data set, so that if we train our model on that small subset, we hopefully get similar performance. Okay, so these are the types of problems that received a lot of attention. There's lots of concrete objective functions that quantify notions like relevance, diversity, reliability for these types of problems. You've seen some examples in the first part. I will not discuss too much concrete examples of these problems. So this is the motivating examples. But there's many more applications of submodular function maximization. Stephanie talked about several of them before. So some of them arise, for example, in the context of network analysis, right? Identifying most influential nodes in a social network. There's been applications on, for example, recovering social network structure from observing cascading phenomena that have been recorded. There's lots of applications of submodular function maximization in computer vision with applications such as multiple object detection and so on. There's also lots of applications in recommender systems where submodularity acts as some sort of bias towards obtaining diverse sets of solutions. So you don't want redundancy in the recommendations that you make. Okay, so these are flavors of optimization problems where you're looking for a discrete solution and where you might want to maximize notions of utility that capture diminishing returns, that capture coverage, diversity, and so on, that are naturally formulated using submodular functions. Now in the literature of submodular function maximization, there's a big distinction depending on whether the objective function is monotone or not. This point already came up briefly in the first part of this tutorial, so I want to talk about this some more here. So we call a set function f that might or might not be submodular, we call it monotone if whenever it holds that adding some elements to our sets can only increase the function value. Right? So whenever we compare f on some set S with f on some superset T of S, then f of t can only be bigger than f of s. That's monotonicity. Okay, and many of the notions of utility that we've talked about intuitively are monotone, right? So one simple example are coverage functions, right? A simple model of sensing that Stephanie had talked about earlier, cardinality of union, for example. But there's other examples that are non-monotone, right? And as a reminder, one important example of a non-monotone submodular function is the graph cut function, right? So if you take a graph here and you define a set function by taking a set of nodes and counting or the number of edges that connect those nodes with the not selected nodes, then the cut function associated with this set here cuts 3 edges. If you select the superset, you have to cut 5 edges, but if you add even more nodes, you only cut 1 edge, right? So that's an example where it violates this monotonicity condition. So in the first part of this tutorial, we'll focus on maximizing monotone submodular functions. And now the question is, given some submodular function, how can we maximize a submodular function that's also monotone? Turns out that's a pretty easy problem. Well, if it doesn't hurt us to add more elements, why don't we just pick everything? Okay, so the problem of unconstrained monotone maximization obviously is trivial. So it only makes sense if you also have some constraints. So what's the simplest types of constraints? The ones that are studied most widely in the literature are cardinality constraints, where you just put a bound on the number of elements that we can pick. Right, and just at this point here, so in the first part of this tutorial, Stephanie primarily talked about unconstrained submodular optimization problems, unconstrained minimization, which is polynomial time tractable. So here, we'll talk a lot about submodular function maximization under constraints. Okay, so now it turns out that adding this constraint turns this trivial problem into an NP-hard problem. So we'll be looking not for algorithms that obtain the optimal solution, but for approximation algorithms. And perhaps the simplest one, the most well-known one for constrained monotone submodular maximization is the GREEDI algorithm. It's perhaps the most natural algorithm that you might be thinking about, and it goes like this. So what you're going to do is we'll start having no elements, so start with the empty set. Then we're going to score all the elements we can possibly pick, and pick the one that provides us the largest singleton value, the largest gain on top of this, the empty set. If you think about some sort of coverage function here, maybe this red element here covers the most elements in our universe. Now once we've selected this first element, we're going to add a second one. And among all the elements that we can possibly add, we'll add the one that provides as much gain in utility as we can possibly get. Right? So if you have, say, this green and this blue element here, the green element might only cover one additional element, so it gives us a marginal gain of 1, versus this blue element would cover these 8 additional elements, so it gives us a marginal gain of 8, so we prefer this blue element. Right? Then we just greedily add one element at a time, always the one that maximizes this gain in utility. Right? Sort of a very natural algorithm. And if you think about the marginal gain as some sort of discrete derivative, this algorithm looks a bit like gradient descent. Right? I already discussed a lot gradient descent in Elad's tutorial this morning. So you can view the GREEDI algorithm in some sense as some sort of discrete analog, maybe. Of course, now the question is, how well does this algorithm do? And of course, one thing you could do is you could do some experiments, right? And you could actually try to compare it against the optimal solution. So in general, finding the optimal solution is very difficult, but if you take smaller scale problems, you might be able to find the optimal solution using branch and bound type algorithms. So here's an concrete empirical results coming out of an application in optimal sensor placement. Don't worry too much about the specifics. This plot here basically just plots the utility, here this mutual information that Stephanie had talked about in her first part of this tutorial, over the function of number of sensors that we've picked. And it shows the GREEDI algorithm compared to the optimal one, and GREEDI is really close to opt. Now, of course, this is a very specific instance, right? And so it might be lucky, but this is actually fairly consistent on a number of submodular optimization problems that do arise in practical applications, at least in sort of a small enough regime that you can find the optimal solution. Okay, and turns out this is not just an accident, but one can actually prove something about this GREEDI algorithm. Yes, Alexander?
Were there any attempts to characterize what is the property that will improve upon the bound that you were about to say?
So we'll talk a bit about this later. So there's some parametric properties of submodular functions. The most prominent of which is the curvature, which allows you to get sharper guarantees.
Do they explain, for instance, these experimental results, like in this?
Yeah, there's been some work specifically on mutual information where you try to calculate the curvature. For example, you can do this in context of Gaussian processes with specific kernels and so on. So I'm happy to point you to these references. Okay, so, but the general result, and it's perhaps the most well-known, widely known result about submodular function maximization is the celebrated theorem by Nemhauser, Woolsey, and Fisher from the late 70s, who proved that the GREEDI algorithm provides a constant factor approximation, where the constant factor is about 1 minus 1 over e, which evaluates to roughly 63%. And it turns out that's the optimal approximation if you don't assume anything but submodularity. Okay, so if all you are given is oracle access to the submodular function, then in general you need to look at exponentially many sets in order to obtain a better approximation for general instances. So in some ways the GREEDI algorithm is optimal for the general problem of submodular maximization. Of course, in special cases you can do a lot better. So since this is such a central result, I want to at least give you an idea of the proof behind this result. So here's a sketch. So what we're going to do is we're going to look at the value of the GREEDI solution, SL, obtained in the Lth iteration of the GREEDI algorithm, as we keep adding more and more elements. Okay, so this is the GREEDI value. Turns out this is always going to be concave. That actually follows from submodularity. And now let's plot the optimal value achieved by the solution of size k. And what we want to show is that once you've picked k elements, you get at least 1 minus 1 over e of that optimal value. Right? That's what we want to show. Okay, now the way the analysis goes is that you look at the sequence of gaps that are left at each iteration of the algorithm. So delta I is simply opt k minus f of si. Okay, so the amount that you're suboptimal compared to this optimal solution of size k at the ith iteration of that GREEDI algorithm. Okay, and the key lemma that one can show, I'm not formally doing this here, I'd be happy to do it later if you're interested, is what's sometimes referred to as the rate equation, which relates the marginal gain of the GREEDI algorithm at the ith iteration to the gap that's still left. In particular, you can show that at iteration I, there always exists some element e such that if you add it to the current set, you close the gap by at least 1 over k times the current gap to the optimal solution. This result follows from monotonicity and submodularity and implies, via a set of simple steps, the result that we're interested in. So in particular, as an easy consequence, you can apply this definition here to see that the gap at iteration I plus 1 is at most 1 minus 1 over k times the gap at the ith iteration. Now, recursively, that just tells us that the gap at the Lth iteration is at most 1 minus 1 over k to the L times the gap at the 0th iteration, the start of the algorithm. But by assumption, the function is non-negative. Actually, you should have stated that assumption. So we generally talk about non-negative submodular functions. That gap is at most the optimal value. All right? And then if you solve for this, you can show that essentially the value at the Lth iteration of the GREEDI algorithm is at least 1 minus e to the minus L over k times the optimal value of size k. So of course, if you plug in L equals k, this just gives the 1 minus 1 over e, the result from the previous slide. But this result is actually more generally useful, right? So you might, it's a natural bicriteria type result, right? So for example, you might compare the GREEDI solution of size 2k with the optimal solution of size k. So this result actually proves other results, for example, about submodular coverage. You can recover results about the set cover problem from this rate equation. It turns out this relation here, this rate equation, is really central in submodular optimization. It occurs all over the place. So in a lot of the algorithms we'll talk about later, the key why they work in the monotone case is some sort of rate equation like this. Okay, so this is really the most important quantity. So we talked about the, yes?
So it's only true for I up to k, I guess?
It's true for any I. So in particular, you might ask, suppose I want to get the exact value as the optimal solution of size k. How large does I have to be to match that value? Right? Or to match 1 minus epsilon that value, right? And it's useful for these kinds of purposes. Okay? Good. So the GREEDI algorithm, yes?
there a simple function that matches this in terms of tightness?
There are examples. You can actually match it with cover functions. So the 1 minus 1 over k to the L. OK, good. So now the GREEDI algorithm is sort of like gradient descent in the continuous case, right? And that's sort of the GREEDI algorithm here, gradient descent algorithm. So the question now in spirit of gradient descent plus plus, what is GREEDI plus plus? So I took that liberty here to refer to Elad's and Sanjeev's notion of gradient descent plus plus. So there's a bunch of questions you might ask here. So first of all, we talked about cardinality constraints, but in practice there might be other constraints. So what happens there? So let's start with that topic, and then we'll talk about some more here. So what happens if we have more complicated constraints? So what kind of constraints might you consider? So the simplest extension arguably is to replace the cardinality constraint by what's known as a knapsack constraint or a modular constraint. So basically now with each element we associate a cost, a non-negative cost, C of E, and we require that any set we pick has total costs in terms of the sum of the costs of the elements that doesn't exceed some budget B that we have. Okay, so for example, the sensor placement application might be more expensive to place sensors on some locations than others. Or if we say want to summarize a document, we might be given a total budget of characters, maybe at most 140 characters that we can use in our summary. Okay, so now the first thing we could of course do is we could just run the GREEDI algorithm. But of course the GREEDI algorithm doesn't take the cost into account, so in general we shouldn't expect it to do well. The one simple way to take the cost into account is to modify the GREEDI algorithm slightly. And one way to do it, it's arguably the most natural one, is to look at the benefit-cost ratio. So each iteration, we simply greedily add the element E that maximizes the ratio in terms of the marginal gain divided by the cost of the element that we would add. Now it turns out that you can construct instances where both of these algorithms will do arbitrarily badly and provide no approximation. But what can be shown is that the better of those two solutions will always provide an approximation guarantee of 1 minus 1 over square root E. Okay, so it's not quite 1 minus 1 over E. This evaluates to roughly 0.39, so 39%, and will still provide a constant factor approximation. Now the question is, this is a strict generalization of the cardinality constraints, right? If I just have all the costs be equal, then of course I get cardinality constraints. So what about this gap? And turns out you can close it. So there's more complex algorithms that actually provide the 1 minus 1 over E approximation even for these knapsack constraints. And in fact, for a much larger class of constraints. And I want to talk a little bit about that. So there's a very nice algorithmic framework for submodular maximization that can handle a quite rich class of constraints.
So I actually had a question about what you mean by better. Does that mean in each step you pick one or the other, or overall you just use
just overall. So you get two solutions.
the whole thing?
One is just ignore costs, run the GREEDI from before. The other one, run this algorithm. You get two sets.
Okay.
Just pick the better one.
So what if you? Okay. So you could probably use some mix too, but I don't know how you choose which one to use in each step.
Yeah, again, there's different algorithms that will also provide guarantees, right? That's a very simple one, as we'll talk about. A more complex one that also allows you to handle much more constraints than these modular constraints. Okay, and so it's based on a similar idea that has been exploited already in submodular function minimization as presented by Stephanie. So the idea in submodular minimization has been to exploit convex relaxations. Right, you take our set function, which is defined in some sense as points on the associating a value with all the corners of the unit cube. And now what we could do is we could try to extend the function to the interior of the unit cube. Okay, so we're going to use some sort of extension interpolate between the function values and the corners. And now what we're going to do is we're going to optimize this continuous problem. But of course we have to somehow deal with constraints, right? So in the discrete problem we have some constraints. So the question what to do about those constraints. So what we're going to do is we're simply looking at the convex hull of those constraints. Okay, and so the algorithm, the general algorithmic framework, is approximately maximize the continuous function over this polytope, right? This convex hull of the constraints. And that's going to give a fractional solution, and then somehow round it to get the discrete solution back. That's the general strategy, and of course the question is, there's a bunch of questions, right? What kind of relaxations to use, how to optimize it, and how to round. We'll talk just a little bit about that. So in terms of the relaxation, the first attempt might be to use the Lovász extension, but this idea doesn't actually work for the Lovász extension. So Lovász extension is convex. It's very useful for minimization, but maximizing a convex function in general is hard, and there's nothing specifically known about maximizing the Lovász extension. So instead, the extension that's very useful in submodular maximization is it's what's called the multilinear relaxation. And it can also be understood as some sort of expectation, like the Lovász extension, but under a different distribution. So what we're going to do is we'll take a fractional vector, so point in the unit cube, so number between 0 and 1 for all the coordinates, say 0.5, 1, 0.5, 0.2, 0.2. And now what we're going to do is we're going to flip a coin for each of those coordinates independently according to that probability and decide whether to pick that element. So we might not pick the first one. We're certainly going to pick the second one because the probability is 1. This one maybe we also pick, and the last two we don't pick. Okay, that's one random draw. We'll repeat this, and we define the objective basically as the resulting expectation of that random experiment. Now clearly this is interpolates the corners, right? If you just plug in integral vectors here, you're always going to sample the same set, right? But of course in the interior, this expectation might not agree, and in general does not agree with the Lovász extension that we had discussed before. Okay, and so here's just an equations how that extension looks like.
Sorry, what's the difference? So here the independence is the difference.
Yeah, so it's a different distribution according to which the expectation is taken. And actually there's a whole family of relaxations of submodular functions that are defined in terms of different measures that are defined in terms of the fractional allocation. Okay? We'll not discuss this much more than that, but there's some more that can be said. These are two examples.
So again, so for Lovász extension, like you do the same process except you do threshold.
Yeah, exactly.
And here you just do independent.
Yeah, so Lovász extension is some sort of dependent randomization. This is an independent randomization.
I mean, thresholding is just a way to couple them to the same.
Exactly.
Right?
Exactly. Okay, and so now just as a picture, so here's the Lovász extension, which is always convex, and here's the multilinear extension. And turns out this is neither convex nor concave. So it turns out to actually be convex in certain directions and concave in other directions. Talk a little bit about more about that. Now the Lovász extension is very easily computable, basically by sorting, as Stephanie talked about. The multilinear extension in general can only be approximated by sampling, which tends to make these algorithms somewhat slow unless you have special structure in the objective. And again, just to repeat, the submodular minimization, the Lovász extension is very useful for submodular minimization, it's the convex function, versus the multilinear extension is widely useful for submodular maximization. Okay, so let me tell you a bit more about the algorithm for solving the continuous problem, so for maximizing this multilinear extension. And the basic idea goes back to Jan Vondrak, who called this algorithm the continuous GREEDI algorithm. I'll tell you a discrete version of this algorithm, and related to some other algorithms that we've talked about earlier today. And so let me show you an example of this on a ground set consisting of two elements, A and B. And I'm going to plot the domain. Right? So we'll have one coordinate that tells us how fractionally we pick element A, and another coordinate how fractionally we pick element B. Okay, so our feasible set is going to be some polytope P. Right? In general, the convex whole of the constraints for two elements is trivial, but just in higher dimensions, this will become a non-trivial object. And now what we're going to do is we're going to do some sort of Frank Wolf-like algorithm on this polytope. And let me explain it. So what we're going to do is we'll start at 0, which we always assume to be in that polytope. And we're going to look at the gradient of the multilinear extension at that point. Now, instead of taking a step in the gradient direction, what we're going to do is we're going to solve a linear program to find the vertex that solves this linear program in direction of that gradient. And now we'll increment our current solution by some step size gamma in the direction of that vertex. So far, this is exactly the Frank Wolf algorithm, right? That Stephanie talked about earlier and was already referred to in a Lutz talk this morning. Okay, now what's the next step? Well, we have our current iterate x1. So we are going to, again, look at its gradient, solve a linear program to get that vertex. And now what Frank Wolf would do is would take a step along the segment between x1 and v2, right? Some convex combination. So that's not what we're going to do. Instead, we're going to move basically parallel to this line segment. We're going to increment in the direction of that second vertex. Okay, and so we'll take a step, again, of step size gamma in that direction. And we'll do that in total for t iterations, always taking a step size of 1 over t. So it means in the end, we'll have generated a point that's a convex combination of the corners of this polytope, right? So we're going to get the feasible solution, right? That's a property shares with the Frank-Wolf method. Okay. So now another important statement to make here is that the algorithm generally requires that polytope to be what's called downward closed. So that means if you lower any coordinates up to at most 0, you're going to stay feasible. And this also guarantees that every point along the path that this algorithm takes will be feasible, will be inside that polytope. Okay. Now that gives a fractional solution, and that somehow then is being rounded to a discrete solution, which is the output of the algorithm. So what can one say about this algorithm? So it turns out this algorithm works, in the sense described below, for any downward closed solvable polytope P. So that generalizes cardinality constraints and knapsack constraints, generalizes the intersection, right? You might have multiple knapsack constraints. There's other constraints like matroid constraints and so on that all satisfy this property. So it's a fairly rich class of constraints that I don't want to discuss in detail. And it actually not just holds for the multilinear extension, but it holds for a generalization that's called monotone DR, or diminishing returns, submodular continuous functions. So it's an interesting class of non-convex maximization problems that can be solved approximately using this algorithm. Okay, and now what works means, basically means works providing a 1 minus 1 over e minus epsilon approximation where epsilon depends on the step size. Okay, so if you take more steps, you can get closer to 1 minus 1 over e. Okay, now this is solving the continuous problem, so giving an approximation guarantee of solving the non-convex maximization problem over this polytope. And you still have to round it to an integral solution. And now the rounding strategy depends on what kind of constraints there are. And for specific families of constraints, there's specific rounding algorithms. Okay, and the most commonly used ones are pipage rounding for matroids, or contention resolution schemes for more general downward closed polytopes. Okay, I'll just give the reference here. I won't have the time to describe these rounding schemes in detail. Okay, so that's basically the basic results about the GREEDI algorithm. Yes?
Any guarantees on the quality of this rounded solution?
Yeah, the rounded solution will have the same. So all of these rounding strategies here are basically lossless, so you can bound how much loss you can take. So pipage rounding is lossless. So for matroids, you actually get the 1 minus 1 over e guarantee.
You said we have to follow this parallel line in the algorithm. So in order to guarantee feasibility, it seems like we have to calculate where it hits the boundary.
No, you never have to. So it turns out, since we always take a step size of 1 over t, and we take t steps, and every time we move in the direction of a vertex, we always remain feasible.
Yeah.
Okay, good. So that's a pretty rich framework. Yes? Okay, how do you compute a gradient? So that's basically, might depend on specifics on the submodular function. So in general, you'll have to do it numerically somehow. If all you assume is oracle access to the function value, so that's very expensive. For specific types of functions, you might be able to do it more efficiently. Other questions? Okay, good. So now this is a very rich algorithm, right, for solving a large class of constraints. Now on the next topic, let's actually go back to the simple problem of cardinality constraint maximization, which is actually widely useful. And actually think about going the opposite direction, right? So instead of solving a richer problem, let's try to see if we can solve that very simple problem, but very fast. So why is that? Well, I told you about some of the motivating examples being data summarization, right? So n, the number of elements in our ground set, might be the elements in some large data set, maybe in the tens or hundreds of millions or billions, right? And k is the number of points in our summary, maybe it's in a few tens of thousands, and so on, right? So even just running that basic GREEDI algorithm might not be feasible. There's actually been a lot of work recently in scaling up the GREEDI algorithm to these types of problems. Okay, and so what I want to talk a little bit here about how to exploit parallelism. So there's been some ideas about this recently. And so now the question is, how can you leverage parallelism to solve the GREEDI algorithm faster? Now one natural idea might be to parallelize the GREEDI selection, right? In each iteration, somehow figure out which next element to add. So we could, for example, take our data set, spread it across a bunch of machines in a cluster, and have each machine in the cluster decide what's the next element we should add. The problem with this strategy is that this strategy requires communication after every single element has been selected. So if you want to select, say, 100,000 elements, you essentially have to synchronize 100,000 times, which can be very expensive. Okay, so the question is there something that's sort of more data parallel, sort of that requires less communication? So ideally what you might want to do is you might want to partition the data set somehow and then find a solution independently at each of these different machines, merge them together, right, in order to somehow find a solution that we output in the end, right? Maybe in one round or a bunch of different rounds and so on. Okay, so the question is what can one do? And now one thing of course you could do is there's m machines, maybe each machine picks k over m elements, and in the end you merge them all together to get k elements back. This is easy to see that this doesn't work very well because they don't coordinate, right, and sort of the systems are very independent. Now instead what you might do, and as a simple modification, is just have each machine select a feasible solution, so a set of size k, merge them all together to get a solution of times m times k, and then run the greedy algorithm again on that reduced ground set size to sort of filter it. Okay, so that's a very simple strategy, and the question is, what can one say about this? Now it turns out, without making some assumptions on the objective function and about the partition, this algorithm will not do well. So it will scale only roughly as sort of a fraction of 1 over m, where m is the number of machines, right, of independent subproblems we solve. But it turns out, under some additional assumptions, the simple strategy can actually make to be work very well. So in particular, if you slightly modify that algorithm and not just consider that solution, but the best one among this solution and the m independent solutions, you can actually show that this resulting solution will actually provide a constant factor approximation as long as the data set is partitioned randomly. Okay, so if the partition of the data set on these m machines is done uniformly at random, then this simple, completely independent operation here actually produces a constant factor approximation. Turns out one can get even better results if the objective function has some specific structure. Okay, and so here's just some empirical results about this algorithm. The x-axis here is the degree of parallelism, so how many machines to use, and the y-axis essentially compares this distributed algorithm against the centralized greedy algorithm on a small enough instance where you can actually run the centralized greedy algorithm. The specifics of the application don't matter too much here. That's a data summarization application. Okay, and so the first baseline is to just select the elements completely at random, and so here's some other baselines that vary in terms of what kind of aggregation they use at the different levels. And so the last one here is this distributed greedy algorithm I described before, and it provides solutions that are virtually indistinguishable to the centralized greedy algorithm. So this works really well. So this is one recent result about large-scale submodular maximization. But there's actually a lot of other work on solving submodular maximization problems at very large scale. So there's ideas of accelerating even just the sequential greedy algorithm. There's a lot of work on streaming submodular maximization, work on some sort of filtering type approaches where you would use cheaper objective functions first to filter out the ground set and then use more and more expensive approximation to the cost function to produce the final solution and so on. So there's a lot of work on this recently that I give some references to here, but I can't cover in more detail. So the last point I want to discuss under this greedy plus plus category is to talk a little bit about the non-monotone case. So far, as a reminder, we've talked about monotone submodular maximization. So the question is, what happens in the non-monotone case, right, where this inequality here is violated, right, where the objective function goes down and goes up and then goes down later. Now, the first observation is that in general, if you don't make any assumptions on this function f, this problem is really hard. It's inapproximable. And the reason is that it becomes NP hard to just decide whether the sign of the optimal solution is plus or minus, if it's greater or smaller than 0. Okay, so in order to get any meaningful approximation results, you basically have to assume that the function is always non-negative. So all the remaining results are under this additional assumption. Right, and remember the cut function satisfies this condition. And there's some other important examples that satisfy this condition as well. And so the first question is about what if I don't have constraints, right? So in the first part we talked about unconstrained submodular minimization. Now there's unconstrained submodular maximization, and of course if it's non-monotone, that's a non-trivial problem. And so the question of what's the optimal approximation actually was recently resolved by a very nice algorithm called the double greedy algorithm, described in this paper by Buchbinder, Feldman, Nauer, and Schwartz. which actually gives a half approximation, and that's optimal. Okay, so that's sort of the 1 minus 1 over e analog of unconstrained submodular maximization. And the algorithm is also very efficient and actually quite practical. And similarly, there's quite a bit of work on constraint maximization. So it turns out there's a variant of the GREEDI algorithm called the randomized GREEDI algorithm that gives approximation guarantees in the even in the cardinality constraint case. And there's also algorithms that rely on optimizing this multilinear extension that we had talked about a couple of slides ago. But you don't use this continuous GREEDI anymore, but some other variants to optimize this continuous submodular function. Okay, and there's also work on distributed algorithms for non-monotone maximization. Good, so that's basically just to summarize what we wanted to discuss for submodular function maximization. So there's lots of applications. The general problem is NP hard, but GREEDI-like or local search-like algorithms tend to work, and the fairly rich classes of constraints. There's an important distinction of whether the function is monotone or non-monotone. The resulting algorithmic techniques are sort of different. And there's quite a bit of work on solving submodular maximization at very large scale. And now here's just a summary slide contrasting submodular minimization and submodular maximization. So unconstrained submodular minimization is really the only case that in general is tractable, so it's polynomial time solvable. So in general, constrained submodular minimization is hard, and unconstrained and constrained submodular maximization are difficult as well. Okay, but there's a lot known about approximation algorithms for those three hard cases. And in the minimization case, there's these two flavors of algorithms, these combinatorial algorithms and algorithms based on convex optimization. In the maximization setting, there's these GREEDI-like or local search algorithms, as sort of analogs of the combinatorial algorithms, right? And continuous algorithms optimizing the multilinear extension. In both cases, these continuous extensions are very useful, the Lovász extension versus this non-convex multilinear extension. And in both cases, there's a lot of work on solving these problems at large scale, exploiting special structure.
I have a question.
Yes?
It wasn't clear to me that the results in the distributed case, will it apply to any monotone function, or there are requirements on the further requirements on the function?
So the 1/2 times 1 minus 1 over e approximation holds for any monotone submodular function. So no additional constraints. Good. Okay, so that's what I wanted to talk about for submodular maximization. Now, in the remaining part of this tutorial, I want to talk about some advanced topics in submodularity. And the first is what's called semigradient methods. Yes?
You mentioned that for maximization, the extension we use is concave in some direction and convex. Is there any relationship between the regions of concavity and convexity and the path followed by this?
Yeah, so I should have mentioned this. Thanks for getting with this. So it turns out that this continuous GREEDI algorithm always exploits concave directions. Okay, so all non-negative directions are concave, and all non-positive directions are concave. So that's what it explains. Thanks. Other questions? Okay, good. So let me talk a bit about the semigradient methods. So it turns out they're very useful for submodular optimization, but also for other topics like learning submodular functions or doing probabilistic inference with them. Let me start by talking about optimization, because that's been the topic so far, and it's the main theme for today. And so let's get back to this general discrete problem that we want to optimize, so maximize or minimize, some discrete function, f of s, subject to some constraints. Right? That summarizes essentially everything we've talked about in this tutorial so far. And now there's actually a number of interesting cases where this problem is very hard, even if f is a submodular function, but where the problem becomes very easy if the function is not submodular, but just a modular function, just an additive function. Right? So that's the definition of a modular function again, right? That's basically just this sum of weights function that we've discussed. It's always represented by some vector w in Rn. Okay, so there's many examples of this, basically all the basic algorithms that we discuss in discrete algorithms classes. Like, for example, maximum spanning trees or maximum matchings, minimum cuts in graphs, shortest paths, and so on. We can always think of them as solving some modular optimization problem. For example, in the minimum cuts, our cost function is the sum of costs of the edges that we cut. In the maximum spanning tree, it's the sum of the weights of the edges in our spanning tree and so on, right? And all these algorithms can actually be optimally solved for these sums of weights, these modular cost functions. But if you replace these modular cost functions by submodular functions, the resulting problem becomes difficult. Okay, so the question is, can one somehow make use of the fact that we can solve these modular problems efficiently in order to solve the resulting submodular optimization problems? And that's one of the primary uses of the semigradient methods. So we are looking at a general strategy like this. So we'll start with some initial guess of our solution. Now what we're going to do is we're going to try to find a modular approximation, some sort of linear approximation to the submodular function at that current set S. Then we're going to use that black box to optimize that modular function to get the new set, and then we iterate until we've converged. So that's a very natural type strategy that might you consider. And of course the question is, does this work, right? And which kind of modular approximation should you use? And that's the point where we can come back to the connection between submodular functions and convex as well as concave functions. So one characterizing property of convex functions is the existence of subdifferentials. Right? So if you take any convex function at any point x, we can efficiently find at least one linear lower bound tight at that point x. Turns out the same holds for submodular functions. So if you take any submodular function, f, and any set S, you can find efficiently at least one modular lower bound that globally underestimates f, but it's tight, so it agrees with f at that point S. That's just given by this equation on here. Okay? It turns out submodular functions are also sort of like concave functions. It turns out the opposite holds as well. They also have superdifferentials. Okay, so this was observed in a very nice paper by Richard Pierre, Steffi Egalka, and Jeff Bilms a couple of years ago, where they show how to use that idea for optimization. Okay, so you can not just find tight modular lower bounds, but also tight modular upper bounds. And finding means you can construct them efficiently. Yes?
How can you have both at the same time? Because
yeah, sort of this picture is a bit misleading here, right? So in the discrete setting, right, you deal with n-dimensional objects, right, and they can actually do this. Okay? Good, right? And this now, of course, suggests, right, using this previous algorithm, if you want to maximize, always maximize the modular lower bound, and you'll monotonically improve the objective. If you want to minimize, repeatedly minimize a modular upper bound, and you'll be guaranteed to improve. Now, how do these sub and super differentials look like? So it turns out they're actually not unique. So they have some nice polyhedral structure. So that's a picture of the subdifferential of a submodular function at different sets. So here's the subdifferential at the empty set for some specific two-dimensional submodular function. And this shape might look familiar. It's actually exactly the same that Stephanie talked about when she discussed the submodular polyhedron. So the subdifferential at 0 is exactly the submodular polyhedron. Okay, but you can define subdifferentials at any set. It turns out you can do the same thing for superdifferentials as well. So here's the resulting picture for submodular superdifferentials. Okay, they're not quite as nice algorithmically, but one can still construct certain members efficiently. Okay, and now why they're useful, so it turns out you can actually recover essentially all the results about submodular maximization that we've discussed here through this lens of semi-gradient based optimization if you choose the subdifferential in the right way. Okay, so you can view it as some sort of generalization of the results in submodular function maximization through this lens of subdifferentials. But it's also algorithmically very useful and allows you to handle more complex constraints of the kinds that we've discussed, right? Cut constraints, matching constraints, tree constraints, and so on. And now, in general, those problems are very hard to approximate for arbitrary submodular functions. And so the flavor of the approximation guarantees, in some sense, depend on how close the submodular function is to a modular function. And that's quantified using this notion of curvature that briefly came up earlier in this tutorial. And so the curvature basically quantifies how far a given submodular function is from being a modular function. And it's defined in terms of this equation here. So you look at all possible elements in your ground set. and you compare the smallest possible gain associated with that element. That is basically when you get it to the set containing everything but the element j. That's the numerator here. And you divide it by the gain of that element if you add it to the 0 set. Right? By submodularity, the enumerator is always at most as much as the denominator. If it's modular, this is always, the ratio is going to be 1, so the curvature is 0. For a general submodular function, this gain might be 0, whereas this might be non-zero, and hence the curvature actually becomes 1. Okay, so it's a parameter that ranges between 0 and 1, and the semigradient methods and actually more general results about submodular maximization and minimization can be improved for functions that have bounded curvature.
Here you assume monotonicity, right?
Yeah, so this is defined for monotone submodular functions.
So this curvature is worst case over all points.
Worst case over all points. You can, there's refined versions of curvature at certain sets and so on. I don't want to go into that, but it's a good observation. Exactly. Okay, and so the kind of guarantees roughly can be, sort of, if you want to remember one thing, it's basically roughly 1 over 1 minus kappa. Okay, so if kappa is sort of very close to 1, these guarantees are not so good, right? But if the curvature is bounded away from 1, right, not too far away from a modular function, then you actually get constant factor approximation guarantees. There's lots of nice applications in computer vision. I won't have time to discuss those in more detail, but to solve very challenging segmentation problems, but also for submodular maximization, for example, informative path planning and so on. We have very complicated combinatorial constraints that this viewpoint allows you to handle. It's also very useful for dealing with these probability distributions associated with submodular functions. And I want to just talk about this a little bit. So Stephanie already talked about these log submodular and log supermodular distributions in the first part of her tutorial, right, which generalizes things like attractive Ising models in the log supermodular case, and determinantal point processes in the log submodular case, and so on, right, capturing notions like repulsion and attraction in probabilistic models. Okay, and so the question is, we've discussed a lot optimizing submodular functions, so maximizing and minimizing them. So what about the resulting distributions, right? Can we do inference in these resulting distributions? Okay, in both the log sub and supermodular case. Inference can mean many things. It can mean sampling from those distributions, but it can also mean things like computing marginals, right? The probability that some element is in my set or not. Now the key challenge in probabilistic inference is to normalize the distribution. That means computing the partition function, right? Which is just the sum over all configurations S of the exponentiated energy function. And that problem in general is sharply hard in both the log sub and supermodular case, and there's some hardness of approximation results as well. Okay, now the question is there anything that can be said about sort of approximations to probabilistic inference? It turns out this is where the semigradient perspective is actually really useful. In particular, you can use it in order to do some kind of variational inference to obtain bounds in a partition function. The basic idea is actually very simple. So we discussed how given any submodular function f, you can obtain modular upper bounds and modular lower bounds of that function, right? So modular functions that are global overestimators and global underestimators, right? And actually, that's not just one, but a lot of them, right? Depending on where we linearize and which member of the subdifferentials we pick. Okay, so we can construct the collection of bounds, upper and lower bounds, on that function. That means if we want to compute the partition function of f, we might just, well, compute the partition function for these upper and these lower bounds, right? We just need to compute the partition function of these associated log modular distributions, right? Plug in these modular approximations to the objective function. But if you exponentiate a modular function, what do you get? Well, a modular function is just a sum of a bunch of terms. If you exponentiate that sum, you're going to get a product. Right? So you just get product distributions, and those are, of course, easy to normalize. Right? You can compute basically upper and lower bounds on the partition function of these probabilistic models by normalizing these sub and super gradients. Now, of course, you not just want any bound, but you want the best bound. So you want to optimize over those. And this is where you can exploit submodularity. You can exploit this polyhedral structure of these sub and super differentials in order to optimize these upper and lower bounds in the partition function. I will not have the time here to discuss those details, but I'd be happy to talk with you offline about them. There's a lot of nice connections actually to optimization problems that Stephanie talked about earlier in her tutorial. For example, connections to the min-norm point problem. Okay, it's just some illustrations of where this is useful. So Stephanie talked about image segmentation, right? Semantic segmentation, identifying the set of pixels associated with the target class, being an important example of a submodular optimization problem. Okay, now, if you solve submodular optimization, you basically find the mode of the distribution, right? The maximum a posteriori configuration, right? So this is a concrete example here where it's ground truth image, the ground truth segmentation, and this is sort of the map solution, the point estimate, the mode of the distribution. Okay? Now, using this variational inference, you can actually also quantify the uncertainty. Actually compute the probability or approximate the probability that any pixel is associated with any given target class. So this just here shows the marginal entropy associated with the marginals at all these different pixel values. Okay? And so here, for example, in this case, the map solution makes a mistake, right? It sort of merges the car with this object in the background here, but at the same time also very uncertain about this prediction. Okay, so this is what I wanted to talk about in terms of semi-gradients. In the last couple of minutes, I want to talk about another topic that is connected to this notion. So one of the themes of the Simon's program is interactive machine learning. And I want to talk about some of the roles that submodularity might play in this area of interactive learning. And to do that, let me start with the following examples. We discussed that one of the motivating examples of submodular maximization is optimal information gathering or active learning, right? Optimal information acquisition, experiment design. Okay? Now, in that setting, it's very natural to not just look at subset selection problems, but look at some sort of adaptive planning problems. So think about the following scenario. Suppose we are a veterinarian and we'd like to diagnose the sick puppy here. So the first thing we might do is we might measure the puppy's heart rate, and if we find that the puppy still has a heart rate, then we might do an ECG, and depending on what we see on that ECG, we might take a blood sample. Now depending on that blood sample, we might decide how to treat that puppy. Now if he had seen something else on that ECG, maybe we should have done an MRI instead. Okay, so you can think about this problem here of choosing which tests to perform as some sort of subset selection problem. In the end, we want to pick a set of tests. We don't want to do all of them. We don't want to waste the puppy's time, right? So we also want the test to be informative, right? You want the tests to depend on all the observations we make along the way. So it's not just a fixed set that we pick, but if you pick an element, you observe something about that element, you pick another element, observe something about that element, and so on. Right? It's similar to, if you think about active learning, right? You pick an unlabeled example, get to see the label. Depending on the label, decide which next element to pick. Okay? Now it's sort of like a subset selection problem, but we somehow want to take interaction into account. And the question is there some notion of submodularity that we can apply to these types of sequential decision problems? It turns out there is. So I won't discuss this in a lot of detail, but basically here's a model in which you can think about this. So we still want to select sets of items, so one item at a time, but we now want to take into account observations we make on those items. So we'll associate with each item in our ground set, which might correspond to a medical test or an unlabeled example and so on, a random variable that governs the outcome of this observation. Right, the outcome of this blood sample, the label of the unlabeled example, and so on. Now we'll have some objective function which depends both on which sets we pick and also the state of the world, right? The values that all these random variables take. And what you want is a plan, a policy, decision tree that tells us which next item to pick given all the observations made so far. And we not just want any policy, but a good one. And so there's natural ways to quantify the value of a policy. So if you think about it as a decision tree, depending on what you observe, you take a different path down the tree. And each of these paths has a different value. So the value for policy is just the expected value at the leaves. Okay, now the optimal solution is actually not a set, but a tree. Right? It might be an object that is exponentially large to even write down. And the question is, how can we find a good tree? Right? Say, for example, what's the best tree of size k? Okay. Now, in general, this is a strict generalization of the kind of problems we've talked about so far. So it's certainly NP hard, and it's generally also very hard to approximate. So the question is, are there some sort of sufficient conditions that allow say, greedy algorithms to work. So in order to say this, we first have to discuss what's actually the greedy algorithm here. So what's a natural greedy algorithm? So what we might do is we might generalize the notion of a marginal gain. Okay, so what we're going to do is we look at the expected gain that we could get from carrying out some test S in the context of all the observations we've made so far. Right, that's the conditional expected benefit of adding some item S in the context of having made some observations XA so far. Right, it's a conditional expectation. And now what we do is we basically just greedily maximize this conditional expectation. So we start having observed nothing, then we compute this gain for all the elements, we pick the one that maximizes it, and keep going, and then we observe the outcome of the items that we actually have picked. Right? Observe the outcome of the medical tests that we've run. And the question is, when does this algorithm work? And it turns out there's conditions like monotonicity and submodularity that allow us to make statements about this greedy algorithm. And so they're called adaptive monotonicity and adaptive submodularity, which generalize the monotonicity and submodularity conditions to the sequential problem. Okay, and so in particular, what this adaptive submodularity condition says basically is that if you look at the expected gain of some item somewhere down the tree, and we consider comparing that expected gain with having played that same item, having picked that same item somewhere earlier, somewhere higher up in the tree, then we can only gain more utility. So it never pays off to wait. It's always better to carry out some action earlier rather than later in terms of expected gain. Okay, so it's a generalization of this diminishing returns condition, actually a strict generalization of this diminishing returns characterization of submodular set functions. It turns out that's enough in order to prove similar kinds of guarantees about the greedy algorithm than those that you've seen before. So in particular, you can prove that this adaptive greedy policy still gets this 1 minus 1 over E approximation. And there's a lot of results about submodular maximizations that carry through to the sequential setting. Okay, so there are some nice applications of this. In the interest of time, I'll actually skip those. And I just want to wrap up by saying that there's actually a lot more that can be said about submodular functions and their role in sequential decision making. So for example, there's a lot of interesting work on regret minimization of submodular functions or bandit problems involving submodular functions. There's a lot of work on streaming algorithms for submodular optimization. There's actually notions of submodularity for sequences of items, so for tasks like sequence prediction, for example, and so on. So that's, there's a lot of work in this general area, and lots of interesting problems as well. So that gets us to the end of the tutorial. So just a couple more notes on what we have not discussed. So of course, there's many topics we are not able to talk about. So there's lots of really interesting work on learning submodular functions. So we focus on optimization here. Lots of nice connections to game theory, so equilibria in cooperative and non-cooperative games, mechanism design using submodular functions. There's various generalizations of submodular functions. There's actually a lot of interesting work on solving non-submodular optimization problems using ideas from submodular optimization. Right? Similar to continuous optimization, where a lot of the algorithms that we apply to non-convex problems actually originate from convex optimization. The same holds for submodular functions. So we've seen, hopefully, throughout this tutorial, there's lots of nice connections of submodular optimization and submodularity as a structural property to many areas of machine learning and probabilistic modeling. You've seen some examples in deep learning, sparse reconstruction, interactive machine learning. And that's my last slide. So I hope we've convinced you that there's lots of interesting discrete optimization problems in machine learning, and a lot of those actually have a nice structure that one can exploit. We've talked about how submodularity has lots of nice computational benefits that makes the resulting optimization problems tractable, or at least allows to obtain provably good approximations. It's not just solving these classical optimization problems subject to some constraints, but there's very rich notions of submodular optimization problems, for example, in interactive decision making and so on. So that's it. Thank you.
Questions?
So about the Frank-Wilf light algorithm, which achieves the optimization, say instead of using the Frank-Flag algorithm, you're using something naive like, say, projected gradient, right? And then you run it, and eventually you get trapped at some point, which is like a local optima. And now, if at that point you were to run a Frank-Flag algorithm, it seems like you still get trapped there, right? Because if you take a sufficiently small step in the gradient direction or roughly in the gradient direction, and you're trapped in a local optima, then you won't step out of it. So is the 1 minus 1 over E a statement about the landscape of the function? Or is there something special about the Frank-Flag algorithm that gets you out of?
So the 1 minus 1 over E is specific to this algorithm, in the sense that you can show a similar kind of rate equation that we've discussed for the GREEDI algorithm, just the classical discrete GREEDI algorithm, for this continuous GREEDI algorithm. So you can essentially make certain statements about the amount of gain you get for each step along the path that this continuous GREEDI algorithm takes. And if you use a different algorithm for continuous optimization, it will be difficult to make similar kinds of statements. I'm not aware of an analysis, for example, for projected gradient descent for this problem. I'm not sure if that answers your question.
So the thing is, the analysis of the algorithm and the result very much relies on where you start the algorithm. So you start at 0 and you only go into these concave directions. So if you started at any other point, this basically would be going not in concave directions but arbitrary directions. So there's nothing you could easily show about it.
I see, so the starting point was important.
Yeah, exactly.
About sequential decision making, I was wondering that since the submodular function is a set function, how to deal with that the decision is the same set but with different order. I mean.
So I'm not quite sure I understand your question. So are you referring to sort of what kind of models one might?
I mean,
no.
If we model it as a optimization problem, the variables are decisions.
Yeah.
How about the decisions in different order, but they are from the same set? Then the submodular function just a function about the set, so they should.
So maybe you're referring to sort of submodularity over sequences. So I mean, there are notions of submodularity that one can define over sequences of items. For example, I'm not sure if that's the answer. So for the particular model I've discussed, essentially the sequentiality comes to the particular model of interaction considered, right? You pick an element, and then the resulting random variable is revealed to you, and depending on that information, you get to choose the next element, right? So the next element can always depend on all the information you've obtained so far.
I see. So, I see.
But you still select the set in the end.
Yeah. So the same set, but different value for the function.
Yeah. And as I mentioned, there's also other models that, for example, one can look at online submodular maximization or minimization, right? So talked a lot about online convex minimization, for example, right? Online convex programming. One can do online submodular programming, right? Where every round you pick a different set, and you look at the regret of the resulting algorithm compared to the best set in hindsight. So the result is that way.
All right. Let's thank Andreas again and all of the speakers today.